In this lesson, we will discuss the effects that resistance, inductance and capacitance have on voltage and current in an AC circuit. Current and voltage in an AC circuit have the same frequency, and their waveforms or the shapes of their cycles are the same. In aircraft AC generator systems, the voltage and the current waveforms are both sinusoidal. In a DC circuit, the current flow is directly affected by the applied voltage and circuit resistance in the relationship formulated by Ohm's law, I equals V divided by R. That is to say, the current is directly proportional to the voltage and inversely proportional to the resistance. There are very few AC circuits in which the current is affected solely by the applied voltage and resistance. In most AC circuits, because of the ever-changing values of voltage and current, the current flow is influenced by the magnetic and electrostatic effects of inductance and capacitance. There is no such thing as a pure resistance when considering an AC circuit. All resistors, even a simple piece of wire, have a property known as inductance as well as resistance. However, for the purpose of studying AC theory, we will assume that we can build separate circuits having only resistance, inductance, or capacitance. We will look at the effects that each of these three properties individually has on the voltage and current in an AC circuit. Beginning with resistance. In a theoretical AC circuit containing only resistance, both the current and the voltage pass through zero and reach their peaks in the same direction simultaneously. In such circuits, the voltage and current are said to be in phase. You will recall that by moving a conductor relative to a magnetic field, or vice versa, a voltage is induced in the conductor. You will also recall that the voltage is only induced when the conductor is cutting through the lines of magnetic flux. You also know that when a current is flowing in a conductor, a magnetic field proportional to the magnitude of the current flow is formed around the conductor, and that by winding the conductor in the form of a coil, a magnetic field with lines of flux similar to that of a bar magnet is formed, and the strength of the magnetic field is increased. Movement of the flux around a coil can be achieved without physical motion, by varying the current flow, thereby causing the lines of flux around the coil to expand or contract. We can use this fact to induce a voltage in an adjacent coil. To demonstrate this, we place two coils close together, with one known as the primary coil connected to a DC power supply via a switch, and the other secondary coil connected through a load to a center zero ammeter. With the switch open, there will be no current flowing, so there will be no magnetic field around the primary coil. When the switch is closed, current will begin to flow, and a magnetic field will build around the primary coil. As this field expands out from the coil, it will cut through the turns of the secondary coil, inducing a voltage in it, causing a current to flow. Once the current flow in the primary circuit stabilizes, the magnetic field will also stabilize. The lines of flux will have no movement relative to the secondary coil, and the induced current will fall to zero. When the switch is opened, the current flow in the primary coil will fall to zero, and its magnetic field will collapse. The lines of flux of the collapsing field will now again be cutting through the secondary coil, but this time in the opposite direction, and a voltage and current in the opposite sense will be induced. Once the magnetic field has completely collapsed, the relative movement will again stop, and the induced current will again fall to 0. If we now change the supply to the primary coil from DC to AC, then with an ever-changing and alternating current flow in the primary circuit, its magnetic field will be constantly expanding and contracting. Therefore, there will be a continually induced voltage and current flow in the secondary coil, proportional to the primary coil AC waveform. This is called mutual induction, and is the principle of operation of transformers. If we remove the secondary coil, the AC supply to the primary coil still generates an ever-changing magnetic field, which, as it cuts through the wires of the coil, has the effect of inducing a voltage in the primary coil itself. This is called self-induction, and according to Lenz's law, the voltage induced will oppose the change of current in the circuit. This self-induced voltage is often referred to as the back EMF, or reactance. The ability of a coil to produce a back EMF is known as inductance. There are a number of factors which can affect the magnitude of the induced voltage or back EMF. The more turns of wire there are in the coil, the stronger will be its magnetic field, producing a larger back EMF. Placing a soft iron core inside the coil will produce a stronger magnetic field, with a consequent increase in back EMF. If the frequency of the supply is increased, the rate of change of current will increase, causing an increase in the rate of change of the magnetic field, and again an increase in the back EMF. The effect of inductance in an AC circuit is to cause the voltage and current to be out of phase. Because the back EMF opposes the current flow, the current lags the voltage. In a circuit having only inductance, the current lags the voltage by 90 degrees of phase. Any device having inductance can be referred to as an inductor. The unit of inductance is the Henry, and its symbol is a capital L. A circuit has an inductance of 1 Henry if a current change of 1 amp per second induces a back EMF of 1 volt. Inductance is usually expressed in millihenries or microhenries, as the Henry is too large a unit for practical use. 1 millihenry is 1/1000th of a Henry, and 1 microhenry is 1/100000th of a Henry. Capacitance is the ability of a circuit to store an electrical charge. A device used to introduce capacitance into a circuit is known as a capacitor. Capacitors are fully explained in the DC series of lessons. You will recall that a capacitor consists of 2 plates separated by a dielectric, which can be, amongst other things, air, mica, or waxed paper. 3 factors affect the amount of charge a capacitor can hold. They are the area of the plates, the distance between the plates, and the type of dielectric used. The capacitor will store an electric charge, much like a hydraulic accumulator stores fluid under pressure. But first, it needs to be charged. When connected to a DC power supply, electrons will be removed from the plate connected to the positive terminal and added to the plate connected to the negative terminal. Conventional current flow will be from positive to negative. This process will continue until the plates become saturated, when no more current will flow. The potential difference between the plates is at its maximum, and the capacitor is now fully charged, its voltage being equal to the input voltage. If the capacitor is now removed from the supply, it will retain this charge until it is connected to an external circuit, when the surplus electrons on one plate will flow through to replace the shortfall on the other. Notice that the capacitor has discharged in the opposite direction to which it was charged. Remember that electrons do not pass between the plates through the dielectric. When fitted in an AC circuit, a capacitor will be constantly charging and discharging, as the applied voltage is constantly reversing polarity. As the applied voltage falls, the capacitor discharges current back into the circuit. This has the effect of shifting the voltage out of phase with the current, and in a purely capacitive circuit, the current will lead the voltage by 90 degrees. The unit of capacitance is the farad, F. In terms of capacitance, the farad is a very large unit. 1 farad capacitor could be as large as a soft drink can. The farad is therefore subdivided into smaller, more convenient units. 1 microfarad is 1/millionth of a farad. 1 nanofarad is 1,000th of a millionth of a farad. And 1 picofarad is 1/millionth of a millionth of a farad. Capacitors are also rated by their working voltage. This is the largest DC or peak AC voltage which can be applied across the capacitor. It is usually marked on the case of the capacitor, and if it is exceeded, the dielectric may break down, permanently damaging the capacitor. A useful mnemonic for remembering the relationship between voltage and current in inductive and capacitive circuits is the word civil, where C stands for capacitance, I for current, V for voltage, I for current, and L for inductance. So in a capacitive circuit, current leads voltage, and voltage leads current in an inductive circuit. That is the end of the lesson. Here is a summary of the most important points. In aircraft AC generator systems, the voltage and the current waveforms are both sinusoidal. In a theoretical AC circuit containing only resistance, the voltage and current are in phase with each other. The unit of inductance is the Henry. The symbol for inductance is a capital L. In an AC circuit having only inductance, the current lags the voltage by 90 degrees of phase. The unit of capacitance is the farad. In an AC circuit having only capacitance, the current leads the voltage by 90 degrees of phase.